A right triangle whose hypotenuse is the square root of 7 inches long is revolved about one of its legs to generate a right circular cone. Find the radius, height, and volume of the cone of greatest volume. So think about a picture here to start. So we have a right triangle whose hypotenuse is the square root of 7 inches long. And so we take this right triangle here and revolve it about one of its legs to produce a right circular cylinder. So in revolving it, we create not a right circular cylinder, we create a right circular cone. And so we can see here from that center point to any point on our circle is the radius, and then we have that our side length here is the square root of 7. And so we're asked here, we want to find the radius height. So here is the height of our right circular cone. And so we want to find the maximum radius, height, and volume of this cone. So we know that the volume of a cone is defined as pi over 3 r squared times the height. And so we want what's the maximum volume, what's the maximum radius, and what's the maximum height for this cone. And this is our objective equation. So in order to start differentiating here, we need to rewrite this objective equation in terms of a single variable. So we need to define a constraint. And we can see our constraint equation by looking at the picture of our triangle that we started with. Right, by Pythagorean's theorem, we know that the sum of our two shorter sides, the height and the radius, will equal the square of the longer side, our hypotenuse. So we can say our constraint equation by Pythagorean's theorem is going to be the radius squared plus the height squared is equal to the square root of 7 squared. And now looking at our objective equation, we see it contains a r squared, just like our constraint equation. So we can solve our constraint equation here for the radius squared. So we have r squared is equal to 7 minus our height squared. And so we can now use or take our constraint equation here and plug it into our objective equation to rewrite volume in terms of just height. So our volume equation now becomes pi over 3 multiplied by 7 minus the height squared multiplied by h, and we can simplify by distributing h through to both terms, which leaves us with pi over 3 multiplied by 7 times h minus h cubed. And now we're ready to find the critical points, to differentiate, set that derivative equal to 0, and solve for h. So we have the derivative of volume will be pi divided by 3 multiplied by 7 minus 3h squared. So go right ahead and set this equal to 0, and we can multiply both sides of this equation by that constant 3 over pi, the reciprocal of our constant. And we're left now with 7 minus 3 times the height squared is equal to 0. And solving for h here, we have 3 times h squared is equal to 7, which gives us h squared is equal to 7 divided by 3. And taking the square root of both sides, we are left with height, or h, being equal to plus or minus the square root of 7/3. And since we know that dimensions cannot be negative, we can deduce that our height here must be equal to the square root of 7/3 inches. So we have that maximum height, and we can now use this to find the max, or the largest radius. So again, we know from Pythagorean's theorem that we have r squared is equal to 7 minus our height squared. So we can plug our height into h. So we have the radius squared is equal to 7 minus the square root of 7/3 squared. The square and the square root cancel each other out. We're left with 7 minus 7/3. And we want to get a common denominator. So we can think of 7 as being 7 over 1, and we'll multiply the numerator and denominator by 3. So we have 21 minus 7 over 3. And so our radius squared is equal to 16 divided by 3. And again, taking the square root of both sides here, we're left with r is equal to plus or minus 4 divided by the square root of 3. And for the same reason as above, since dimensions cannot be negative, we can say that the maximum radius is 4, or positive 4 by the square root of 3 inches. So these are the dimensions that that yield a maximum volume. And we're able to conclude that the maximum volume is going to be pi over 3 multiplied by our radius squared. So if we look back up here, we know our radius squared is the square root, is just 16 over 3. Again, the reason that we're using the radius squared is we're substituting into our volume. So I have, again, volume is equal to pi over 3 multiplied by 16 over 3 for the radius squared, multiplied by the height, which is the square root of 7/3. And so we're left with a beautiful final answer here of pi times 16 all over 9 times the square root of 7/3. And this is inches cubed.